All right, our final portion of chapter 5 coming right up. We have a discussion of a whole new deal here called the index of hydrogen deficiency. And it is just a way of looking at a formula and asking ourselves, what are the possibilities for unsaturation or rings? Making a pi bond in a molecule that used to be C4H10, which is saturated, and making a pi bond instead means you removed two H's so you could make the pi. Every time you remove a pair of hydrogens, we say you have created an IHD of 1. So it's always pairs of hydrogen you remove to make either pi bonds, or if I remove this H here and this H here and connect the carbons on the end, we get a ring, and we also get an IHD of 1 as evidenced by the formula. So IHDs are caused by either rings or pi bonds, or both. This one has an IHD of 2. We made a pi and a ring. This one also has an IHD of 2. It has 2 pi. And there we go. And these have IHDs of 2 and 3. Look, this has 2 pi's. Remember, the first bond's a sigma, and the others have to be pi. So 2 pi's there, 1 pi there, total is 3. So we're never going to be looking at a picture of a molecule and be asked the IHD. We're always going to work from the formula and figure out the IHD from that. So let's do a simple example here, and we'll do our own example over here. We'll do C22H30. And what did we do down here? What is the IHD for C12H18? Well, first job is to figure out what is the saturated acyclic versions formula. That means no pi and no ring. And that's 2 times 12 plus 2. 2 times 12 is 24 plus 2 is 26. Then you subtract the formula. If it doesn't have just C's and H's, we're going to have to correct the formula, which we'll do down here. But this one has just C's and H's to start with. So you take your C12H26, the saturated acyclic right there, and you subtract the one in the question. You get a difference of 8 in this question, and you divide by 2 because it's always pairs of hydrogen. Your answer is 4. So we're going to do our own right here. What's 2 times 22? It's 44. Add 2. H46. Subtract. 16 divided by 2 is your final answer is 8. So this molecule over here could have 8 rings. It could have 7 rings or 1 pi bond. It could have 6 rings and 2 pi bonds. It could have 5 rings and 3 pi bonds. Should I go all the way to the end? No. The end would be 8 pi bonds, 0 rings. There. Now, what do we do if there's elements other than C and H? Let's blow this up. We just need to look at what they do to an actual molecule. Remember the C4 molecule without pi, without ring is 2 times 4 plus 2, C4H10. Well, when we brought an oxygen into the formula with C4, it still has H10, and look, there's no rings or pi, so whatever we do, the theme of the day for oxygen is all day, ignore it, whether it's terpene questions or here. And it's not just oxygen, it's the whole column on the periodic table. Oxygen, sulfur, selenium, and tellurium. So when you see any of those elements, you ignore them and just keep the C's and H's. Then do it from there. What does a bromine do to the formula? Well, it took the place of an H, didn't it? It bonds like H. So this thing went down to H9. We want to get rid of the Br and correct it to just C's and H's. We got to put an H back on. There you go. So what do you do in the halogen column? You add 1 for each halogen. Go to the left. What does nitrogen do? Well, nitrogen brought an extra H into the formula. Look, it went up to 11. Every time you have a nitrogen, what do? You subtract 1 from the formula. There's the correction. The correction better be the same for all of these because they're all saturated acyclic C4 molecules. So there you have it. I think we'll just finish this part with these examples, and if we get these answers, I think we're comfortable. How do you correct this formula? Oh, that's not what I wanted. It's kind of cool. That's going to be C11H22. Why? Because each fluorine has to be replaced with a hydrogen. The normal C11 is H24, 22 plus 2. Subtract, you get H2 divided by 2 equals answer 1, which is over here. It's good. This one corrects to the nitrogen. You got to subtract an H. That makes you get down to C5H4. Normal C5 is C5H10, 12, sorry. 2 times 5 is 10 plus 2 is 12. Subtract, you got H8 divided by 2. You get your answer 4. This one, you got to lose 1 for each nitrogen. So you're down to 23 and then gain 1 back to 24 for bromine and then ignore sulfur. Sulfur's up here. And so I think we went from 26 down to 23, back up to 24. C26, H24. What's 2 times 26? 52 plus 2, 54. Subtract, you get H30. Divide by 2, get 15. I think we've mastered IHD. There we go. So if I add a 7th question to the multiple choice, I don't think anybody would object if it's IHD. I'm only going to say it here. It's not on the study guide. So just tell your friends, study that IHD. That's going to be one of the easier multiple choice questions, isn't it? Yeah, do that. Okay. Finishing up with physical properties of alkenes and then chemical properties. These are both short, so we will get done in time. The properties of alkenes are very similar to alkanes. They have densities of less than 1 gram per milliliter, so they float when they're spilled in water. They're mostly colorless. They have low boiling points and melting points because they have low strength intermolecular forces, London only. CCC is not a polar bond at all, is it? Branched alkenes will have weaker intermolecular forces than unbranched alkenes of the same mass. So that's the same as alkanes. They don't dissolve in water. It's all boring. Cis versus trans, there's a slight effect on the boiling point and the melting point because the trans molecules can get in with each other pretty tight. They have higher London forces, and the cis molecules are more like a ball. It's hard to get them on top of each other. But the trans are like kind of like this, and they look at how nicely they can nestle on each other. But the cis, like, they're bumping into each other. So there you go. And it's not a very big difference. It's only a few degrees, but it is something. So that's all we need to say about physical properties of alkenes. I don't think there's going to be a test question on that at all. Just too dull. But this is going to become increasingly important, not only here where it's introduced, but in chapter 6 when we get there. So I'm going to talk about it. And there's a nice question as an illustration here. Why does cis-2-butene give off a slightly higher amount of heat than trans-2-butene when it burns? So I want you to totally ignore what we talked about boiling points and melting points. Are those chemical processes? No, those are physical processes. So you talk about intermolecular forces. Here we're talking about molecule stability. And why does one give off more heat than the other? Because they have the same formula. They're going to give the same products, right? I flipped this upside down over here because the answer is upside down. I like doing that. So they're both C4H8 becoming 4 CO2s and 4 H2Os using 6 oxygens. But one gives off a little more heat than the other. And the only explanation could be they're both ending at the same potential energy with the same CO2s and waters. They must start at a different potential energy because delta H is the beginning energy to the end, right? Or end minus beginning, as you learned back in the day. And the question now is, why is the cis giving off more heat? And the answer is very simple. It's less stable than the trans. And why is it less stable than the trans? Let's move this out of the way. We've got a C with 3 H's. Don't we have a word that says these are close together, so they're bumping into each other almost? Yes, it's called steric hindrance. Steric hindrance is a nice end of chapter item that reviews things like eclipsing. That was a form of steric hindrance. Then when we hit chairs, we learned about 1,3 diaxial repulsions. That was a different form of steric hindrance. Here we're seeing cis versus trans, where the methyls are close in the cis and they're nowhere near each other in the trans. They're not bumping into each other. They don't even know if the other guy exists. They're so far from each other. So which one's a little more stable? The one where the groups are farther apart. So that's one thing. And the other thing, which is even more important, it's not really related to this question up here. So let's make sure it's definitely separated from it. If you're comparing a double bond like this one to, say, this one, it's not about cis and trans anymore. It's about the fact that this double bond has 2 groups on it that are carbon. This double bond over here has only 1 group that's carbon. So does this one. Double bond has only 1 group that's carbon. For a reason you will learn in chapter 6 called hyperconjugation. Both of these are less stable than all of these. It's not about cis-trans. It's about how many carbons are attached. And this one has no carbons attached. This is a very unstable alkene. These alkenes have as many carbons attached to the pi bond carbons as possible. There's 4 positions and they're all occupied by carbon. 1, 2, 3, 4. Those are the most stable possible alkenes. And the ones with less carbons attached are the least stable. And in chapter 6, this will be very important. In chapter 6, which is all about reactions of alkenes. And when you're talking about reaction stability is an important predictor of which reactions go fast and which ones are slow. And get ready for that, because that's when our semester really picks up. Right now, it's just been fundamentals. Conceptual understanding of organic reactions is in our future, but we have to have the fundamentals first. So please read that email, which directs you to section 3 at Moodle. You need to get on it now, not waiting till tomorrow to study. No, we learned from the first test that's not a good idea. And the problem set will be ready. My goal's Friday at noon. Stay tuned. If I post it before that, you will also get an email saying your problem set's ready to go, but I need to get it ready first. So that brings to a close today's discussion. And test is on chapters 3, 4, 5. Didn't skip any sections. There's no chapter 6 on the test. It is 1 week from today. And good luck getting started studying if you haven't already. And I'll see you later.